So, we now have a chance to go over the answers to the AP Chemistry exam that you took last week. As you can see, Bronsted acids are always Arrhenius acids. No, that's false. There are lots of things that are Bronsted acids that won't qualify as Arrhenius acid. The conjugate of a strong acid is a terrible base. And you can change the value of an equilibrium constant by raising the temperature, but you don't necessarily increase it. Strongest base that can exist in water is hydroxide. If you put a stronger base in water, you simply end up with hydroxides in the conjugate of whatever the acid is, base is. First order reactions always have consistent half-lives. Yep, Lewis acid-base reactions don't involve H plus ions. Well, some do. An H plus ion happens to be a very good Lewis acid. Problem 2. Have a container that has ammonia at 2 atmospheres at 450 degrees. You add a catalyst and you get nitrogen gas. Obviously, you also have to get hydrogen, since that's what you get when you decompose ammonia. Balance the equation, write the K. Since obviously go down the ICE table, we're producing nitrogen gas that takes twice as much ammonia to produce it, and it produces 3 times as many molecules of hydrogen. Put those values in, and you find out that the equilibrium constant, the pressure equilibrium constant, is 440. Which of these is the more acidic solution, lower pH, more acidic solution? Number 1, of course, the one with less base in it is going to be more acidic. Number 2, the one that actually has an acid in it is going to be acidic. Number 3, the Ki would be neutral, but the sodium nitrite would be base. So the neutral solution would be more. And finally, of course, HBr is a much stronger acid than HBRO is, and so that would be the more acidic solution. On to page 2. So on page 2, we have definitions. A buffer. A buffer is a solution that resists changes to its pH when small amounts of acids or bases are added to it. Oxidation is the loss of electrons. Catalyst, anything that speeds up a chemical reaction and is covered unchanged at the end. Standard state is the lowest energy form at 25 degrees Celsius and 1 atmosphere pressure. And a Lewis base donates a lone pair of electrons to form a coordinate covalent bond. Number 5. Given the following equilibrium, what would these changes produce? Well, adding more sulfurous acid is one of the reactants that'll push it to the right. Removing from CO2, that's one of the products that'll also push to the right. Removing some of the lead carbonate, which is a solid, isn't going to have any effect. And finally, raising the temperature is adding heat. Heat's one of the products that'll push it back to the left. On to page 3. And so on page 3, we have the equilibrium acid-base problems. Nitrous acid has a Ka of 6.5 times 10 to the minus 4th. What's the pH of a solution of 0.25 molar nitrous acid? Have the equation, have to write the K, go to the table. We can ignore the water. We have a good acid and good quantity. Solve for X. X turns out to be 1.27 times 10 to the minus 2nd. And that gives a pH of 1.89. Simple. What's the pH of a solution of potassium nitrite? Well, if nitrous acid is an acid, then nitrite is a base. Kw times Ka times Kb equals Kw. So Kb for the base is Kw divided by Ka. So 10 to the minus 14th divided by 6.5 times 10 to the minus 4th. So the Kb is 1.45 times 10 to the minus 11th. Set up the K quantities. The solution is 0.5 molar nitrite doesn't have any nitrous acid in it. The water is 10 to the minus 7th. We can again ignore the water. We got a good quantity of at least an okay acid. 10 to the minus 11th isn't great, but it's way better than water still. Set up the equation, solve for x. x2 equals 2.77 times 10 to the minus 6th. That's, of course, hydroxide. The pOH of that is 5.56, and that makes the pH 8.44 for that solution. And finally, we have the buffer, a weak acid and its conjugate. Rearranged a little bit for the equation. Again, set up the table, put the numbers in, and we find out in this case that x is 1.625 times 10 to the minus 3rd, so that's a pH of 2.90. So, acids and bases. Nomenclature, you should all be good at nomenclature by now. Hydrosulfurous acid is simply H2SO4, an aqueous solution. HClO is either hydrogen hypochlorite, or more correctly, hypochlorous acid. Potassium's K, permanganate MnO4, disilicon hexachloride, and finally, of course, the cobalt-3 sulfite. That's the end of page 3, on to page 4. On page 4, number 8, we start out with a straightforward stoichiometry problem. 2 nitric acid and 1 sodium carbonate get you H2O, CO2, and sodium nitrate. 15 grams divided by 15.99, it's a 1-to-1 ratio. We get 44 grams of CO2, and so in total 6.23 grams of CO2. And so we have a following pH chart. That pH chart shows we have 2 equivalence points where we get sudden drops. So it's a polyprotic acid, and we're ending up close to 13 for pH, so it's got to be a strong base. So it's a polyprotic acid with a strong base. We're looking for a buffer. Where could it form a buffer? Well, we get a nice buffer region just between 1 and 2. That's not one of our choices. The second buffer looks to be at either 5 or 6, and 5 is in fact one of the choices. 3 wouldn't do us any good. That's actually in a transition range. And in the same way, 9 wouldn't do us any good. That's also in a transition range for this. So the only one where you could really make a good buffer out of it would be somewhere around 5. And finally, an indicator that changed from 1 to 3 would be changing the whole time you were titrating the first proton would be useless. 5 to 7, that's a long slope. You're not going to get a sharp angle anywhere in there, so that's useless. It does seem to drop fairly well from 8 to about 12, so 8 to 10 would be good. 11 to 13, no, again, you're ending up with a sloping region that would not be useful. So the best pH would be somewhere between 8 and 10. Again, I'm afraid I'm not going to be able to send the test back to you. You're just going to have to remember what you did on it. And if you have any questions, do feel free to email me. I haven't gotten them all back yet. Once I have them all, I'll grade them all and post grades onto Blackbow so that you can see what you did and what your grade at the moment is. Starting next week, we're going on to the next chapter. So go ahead and read the next chapter on solubility. All right? And talk to you later. Goodbye.